Hope you guys had a good weekend. Um, I have office hours posted for this week. These are the hours. We have office hours Monday through Thursday. Zedong will be from 1 to 2 on Monday. Mine will be 3 to 4, and MEB 236, and online from 4 to 4:30 on Tuesdays. And then Yusen's is on Wednesdays from 11 to 12:30, and MEB 236. And then I'll have one last one on Thursday online only. For the office hours, just use the lecture link. So if you just click on this, it should be open. So I'll join I'll be online through the class link instead. If these times don't work for me, or if they don't work for you, just feel free to email me or the TAs if you want to meet up with them separately, or just email us your questions as well. And then one other thing I want to talk about is midterm 1 and midterm 2. These are going to be our dates for our midterm 1 and 2. I will be posting a exam from last year that you can use as your practice for pacing, and I'll also post the solutions. They'll be similar in format and content. And if we have time and we're good on schedule, I'll probably spend one class reviewing the midterm material for both of these midterms, probably on the Thursday before the midterm. So the midterms are both on Mondays, but I'll probably spend Thursday reviewing the material. Usually for content, if we look at the schedule here, if we have midterm 1 right here, anything covered in week 4, well, that's on Monday, but anything covered on week 3 will probably be left out. So it'll only be up to chapter 5 usually for midterm 1. Oh, there you go. Yeah, it's just chapters 1 through 5, so you don't have to worry about anything on chapter 6 or onwards. Midterm 2, it's not cumulative, so it's going to be from chapters 6 through 8, and then final will just be all chapters are fair game. So, any questions before we get started? Okay. On lecture 1, I have posted an additional example on block diagram reduction as well, so you can go through that. And today we're going to start a math review and go through chapter 2, which is going to be Laplace transform. Hopefully we'll wrap that up by tomorrow, if not today. All right, cool. All right, so today we're going to be talking about this math review in Laplace transform. This math review is going to be covered in ME 564 as well, so at least you'll be able to see it twice. I think math is very important. It's the foundation of all engineering. So today, so in all my lectures in the future, I'll also talk about the purpose of these slides. So sometimes if you feel like you're getting too lost in the technical details, I'll try to remind you the big picture of why we're doing this. So the purpose of this lecture is to review linear algebra and ordinary differential equations in the context of control. So how we use math in the context of control. And then chapter 2, which is about Laplace transform. Chapter 2, it's going to be focused on this tool. It's just a tool that allows us to predict the output for our system. That's what chapter 2 is about when we talk about Laplace transform or inverse Laplace transform. We use this as a tool for predicting output for our systems, and we also use it for looking at the frequency response of these systems. It's a great tool. It's very similar to Fourier transform. So if you have Laplace transform, underneath Laplace transform, it's Fourier transform, which is a specific subset of Laplace transform. Guaranteed that this is an important chapter, and you'll use this in ME 547 and probably other controls courses as well. So this is a fundamental chapter that you should really pay attention to. If you don't understand, just email us and we'll clarify any questions. So we're going to start with linear algebra review, then move on to ODE, and then We might get to Laplace transform today. And so this is going to be a very fast review. And there's one homework problem on it, which is finding the eigenvalues of a 2x2 matrix. Shouldn't be too hard. You can probably find lots of tutorials on finding the eigenvalues, but we'll go through this fast. So linear algebra and differential equations are covered more in ME 564, 565, and specifically ME 510 if you want to go into the deeper side of linear algebra. So we're just going to go through this quick summary, which relates closely with control systems. So we have a set of linear equations given below. We can express this set of linear equations as a matrix. So we can rewrite the equations as follows, where this is our A matrix. This is our variable vector. Oh, what's going on here? Did it go? Yeah, our A matrix, our X vector, and then our solution B. And the reason why we like this form is because of instead of having three different linear equations, we now just have a single linear equation in matrix form. So then basically what we can do is we can solve for this, where if we take the inverse of A, the inverse of A, we basically get this. AX is equal to B. We multiply the left side by A inverse. Then we get X is equal to A inverse B, or A inverse B. And then we get our solution like that. So I have that on the next page. So solving for x1, x2, x3, this is our solution. Where A has to be square and the inverse of A exists, if and only if the determinant of A is not equal to 0. What that means that all the eigenvalues of A are non-zero. So that means A is also full rank. When we say that inverse of A exists, it also implies that this is also full rank. A is full rank, meaning each row is independent from the other row, or each column is independent from the other column because A is square. One thing to note is that, when we wrote A inverse A, X is equal to A inverse B, we took the inverse on the left-hand side, but with matrix multiplication, order matters. So this is not the same as AX A inverse is equal to B A inverse generally. There are special cases where this holds true. Can anyone guess one case? Yep. So if A is the identity matrix, this is true. So if A is identity, so if A is identity, then this is actually true. So then A inverse A X is equal to A X A inverse. Very few cases are like that. So generally just maintain your order of operations, or like the order of when you apply your matrix multiplication, and you'll be good. So one last thing is if we solve for the above equation where the x vector is equal to x1, x2, x3, the solution for the previous example is 2.61 minus 1.15 and minus 0.1538. When it comes to finding the inverse of a matrix on an exam, I will not go past a 2 by 2 matrix. So you only have to find the inverse of a 2 by 2 matrix, which is pretty easy. I'll provide you with the equation for finding the inverse of a 2 by 2 matrix on the exam reference sheet, which you can find in my week 1 modules. So you can see the equations I provide you for the exam. Any questions? Yeah. No, I don't. You can use any calculator. It gets a little I want to say dicey. Yeah, you can use any calculator. Usually I try to write exams such that they're not too intensive on calculating or using your calculators. So it kind of evens the playing field if you have a dumb calculator versus a smart calculator. Usually. Sometimes it's unavoidable. You can't always have clean numbers, but I try to do that. Any other questions? Okay, so this should be familiar, hopefully. So So when we look at that a matrix consists of eigenvalues and eigenvectors. And what I mean by that is, usually with a matrix, we can represent these as coordinates. So think of the eigenvectors, the name vector means direction. So the direction of A. If we have a matrix that's 1, 0, and then 0, 1, we can think of this as our XY plot, where we can think of this as our X column and this as our Y column. So that's our direction. And then eigenvalues as the length of the direction. So how long this direction is. In this case, if let's say now if I change this to 2, we can make this look longer like that. So those are eigenvectors and eigenvalues. Assuming, and this is just math notation, assuming A is in the set of this domain n by n, meaning it just has n by n dimensions and it's square and invertible, then the eigenvalues of A are found using the following equation, where we just take A, the determinant of A minus lambda I is equal to 0. So this here, lambda is a constant, I is the identity matrix, and then the following is true, where A mu is equal to lambda mu, where mu is an eigenvector of A. So just went through a lot really quick. Here, when we solve for lambda is equal to, there's going to be multiple values of lambda. Those are your eigenvalues. So these are our eigenvalues. And then mu is just going to be the corresponding eigenvectors for each of these eigenvalues. And this relation holds true, where A multiplied by our eigenvector is equal to that corresponding eigenvalue multiplied by that eigenvector. And this is the dimension of the eigenvector. It's a column vector. So my question is, like, how does this relate to controls? And I don't expect you to answer that unless you looked ahead on the slide. Well, basically, eigenvalues indicate the stability of our system. So if we have a matrix with one or more positive eigenvalue, it means our system is unstable. So if you have 100 eigenvalues and one of them is positive, the system's unstable. All of the eigenvalues has to be negative for it to be asymptotically stable. There's a special case for when the eigenvalues are 0, which we'll talk about briefly, and more about it will be covered in ME 547. But basically, we want to avoid positive eigenvalues if we want to have a stable system. So why is having a positive eigenvalue? Yeah, so actually hopefully I'll answer that question within the next 3 slides. It has to do with the math solution using eigenvalues. So just a quick definition. So a So in the textbook, the characteristic polynomial equation is a polynomial where the roots are the eigenvalues of a square matrix and is invariant under matrix similarity transform. So the characteristic equation, so basically what it means is that the characteristic equation is this. Characteristic equation is just the determinant of your A matrix minus S times I is equal to 0. So this is the textbook notation. So the textbook uses S instead of lambda. So if you see S, just think of it as lambda in this case for now. And when they say it's invariant under matrix similarity transform, it means that your matrix will not, the eigenvalues of your matrix will not change when it undergoes a similarity transform. And the way I think of a similarity transform is if we, let's say we have our X and Y axis, we just change maybe the direction of the axis where we still have two unique axes, but they're just rotated or maybe scaled in a different size. The eigenvalues will still remain the same. Even if you just rotate it or you change the angles of the of the axes. So I'll write down here. Invariant means eigenvalues stay the same. So I'll just ask, why does the sign of the eigenvalues matter for stability? So we'll look at a first order. Oh, actually, that's coming up afterwards. Sorry. It's going to be coming up in 4 slides. Sorry, not 3. Okay. So just a little bit more jargon. So basically each eigenvector is going to have, or each eigenvalue is going to have a corresponding eigenvector. So here, mu1 will be corresponding to lambda1 for that eigenvalue, all the way to mu n, which is going to be corresponding to lambda n. So this is the relation that is true where, so this should actually have a I here. A minus lambda I multiplied by the identity matrix multiplied by the eigenvector mu I is equal to 0. This is true for all eigenvalues with their corresponding eigenvectors. Then if we put these eigenvector into matrix form, where into matrix T, where we have mu1 all the way to mu n, it's a matrix containing all the eigenvectors of A. And we put all of our eigenvalues corresponding to this into this diagonal matrix. We can decompose A into the following matrix. A is equal to T multiplied by D multiplied by T inverse. So this is just a matrix decomposition. So I guess right here I wrote this equation is so important that it gets its own page. This is a fundamental relationship that allows us to solve a system response by hand. So the reason why we love this form is because later on we're going to need to take, if you were to solve the system response by hand and you were to take this Taylor series of this equation, it's very easy to calculate. Where if we look at, let's say, a squared, if we find a squared of the system, it's pretty straightforward in the sense that we get T d T inverse multiplied by T d T inverse. So these two inverses, or these two matrices, cancel each other out, and you get t d squared t inverse. So if I take this to the nth power, it's going to be t times d to the nth power times t inverse, where d is equal to lambda 1 all the way to lambda n with our zeros in the off diagonals. So then this is a unique property of when you only have values in the diagonal, d to the nth power is going to be equal to lambda 1 to the nth power, lambda n to the nth power with zeros in the off diagonals. It's a really nice property. And this is why we like the decomposition method. Any questions? Oh, sorry, it's not capital N. Thanks for pointing that out. It's going to be lowercase n. Yeah. What do you mean?
It's like minus one and like the after t is like
Oh, okay, I see. I think I understand what your question is, but let me make sure I'm understanding what you're asking. If I were to write this out n times, uh, so we can just ignore basically all of the, there's going to be 1, 2, all the way to n terms. Then we still get, we get t multiplied by d to the nth power multiplied by t inverse, because the t inverse and the t's cancel each other out. They multiply out to be identity. And then so we just end up getting, maybe if I choose a different color, we get 1d, 2d, and then n d's multiplied by itself. Does that answer your question? It's not n plus 1 because we don't start at 0. Yeah, no problem. Okay, so that's the algebra review. So then we're going to move on to ordinary differential equations review, which will tie in how we use linear algebra to solve ODEs. So we have a first order differential equation. And here, this is an example of Newton's law of cooling, where the change in temperature is equal to your heat coefficient multiplied by your temperature minus the initial temperature. And maybe I'll just denote this real quick. This is going to be our temperature. This is time. When we separate our variables, temperature and time, we get this equation here where the change in temperature over the temperature minus initial temperature is equal to our heat coefficient multiplied by the change of time. When we take the integral on both sides, we get ln t minus t naught is equal to kt plus c1. So just some constant. And actually, this should be, I'll release a corrected version of this. K lowercase t plus some constant. And then when we take the exponential on both sides, we get this final solution. Temperature as a function of time is equal to your initial temperature plus some constant times e to the heat constant times your time. And this is where the sign of your eigenvalues will determine stability, because in this case, our exponential, when it's positive, it's a exponential growth. When it's negative, it's exponential decay, which which case will result in an unstable system if you think about our definition from lecture one. Yeah, exactly. Exponential growth will result in unstable systems because it's unbounded. So this is unstable. Unstable because it is unbounded. And in this case here, k is our eigenvalue. This is our eigenvalue of a 1-by-1 system because so we only have one eigenvalue. It's a one-dimensional system. We're only looking at temperature. So positive eigenvalue, it's unbounded. Negative eigenvalue, it's exponential decay and it's bounded. So then this means that this is stable. So this is how differential equations in linear algebra is related to controls. We use the property of eigenvalues to determine stability. Any questions? Yeah. Oh, yeah. So right here, I wrote k times temperature. It's actually k times time. So uppercase T is temperature and lowercase t is time. This is time. This is temperature. I'll define it here instead. Okay, so if we move on to a second order differential equation, if we look at a mass spring damper system now, and we were to derive the free body diagram, here, I'll just derive it real quick on the side here. If we look at the mass here, we're going to define going right as positive. And then our input is the input force F of T. Then opposing that force is going to be the spring constant, K multiplied by X. And then opposing that as well is going to be our damper, which is going to be Bx dot. So then if we were to define this, sum of forces is equal to our acceleration of this mass, mx double dot, which is equal to, no, shouldn't use that. That's confusing. Sum of forces is going to be equal to mx double dot. So the acceleration of this thing multiplied by our input, which is positive and going to the right, f of t. And then our spring, which is going left, so it's negative minus kx minus our damper force, which is minus bx dot. So then if we were to separate everything by the variables, x is on the left side, input on the right side, we get mx double dot plus bx dot plus kx is equal to f of t. So depending on our initial conditions and input, this isn't as simple as a first order system now. If we have various inputs like a constant force, so this is a constant force. This here is a sinusoidal force. And this here is our it's like called a Dirac function. And this is our impulse. So this is our impulse. It goes back to the hammer I brought the other day, where if I were to hit the system with a hammer, it's going to look something like this. So no force, followed by very high increase in force, and then followed by a drop because we stop applying that force. So maybe it's called this delta T of, I can say T of 0, where this is T of 0. This is where we apply that force. Usually this is equal to just one, and we want to scale this Dirac impulse. We just multiply by a constant, so we could say like 3 delta t 0, which means it has 3 units of force or 3 units of impulse applied at t naught. So based off of the based off of our initial conditions and input, we could have various different responses. This thing can oscillate. This thing could have really good damping, so it doesn't oscillate at all. It could have no damping and oscillate to infinity, or keep oscillating but be bounded. Um, or so we have different solutions. So there's 4 possible solutions based off of our initial conditions, and it's these 4. This is called critically damped. And I think this will go more over what each of these mean in chapter 4. This is called overdamped. Um, the difference between critically damped and overdamped is that critically damped shares the same eigenvalue. So this is the shared, like this is the same eigenvalue. So second order system has 2 eigenvalues, and so critically damped systems have the same eigenvalue, and they are the fastest to decay to 0. Overdamped has 2 different eigenvalues, two different eigenvalues. So the reason why critically damped is the fastest to decay is because it only has 1 eigenvalue, while overdamped has 2 different eigenvalues. One eigenvalue is going to be more negative, meaning it decays faster, while the other is slightly less negative, so that decays slower. So you're going to see the decay slower response to be the dominant response. Third one, it's called undamped. So it's exactly what it sounds like. There is no decay. So there's no decay. There's no decay and it's oscillating forever, but it's not growing because you don't see it's multiplied by a exponential. And then the last one, it's called underdamped. So we have oscillation with decay. So it'll start oscillating and it'll grow smaller over time because it's being multiplied by an exponential term. We might not always want a critically damped system because if you ride if your car is a critically damped system, you hit any bump, it's going to be very, very rough. Maybe we want something to be underdamped, so we ride the oscillation just a little bit and we're not feeling every single bump on the road. So I think I asked earlier what conditions will make our solution go to infinity or our output go to infinity. This is when our eigenvalues lambda is greater than 0. That means it's unbounded. So that exponential term here is going to go to infinity. It doesn't apply to underdamped or undamped systems because there is no decay, but applies to the other 3: critically damped, overdamped, and underdamped systems, where when lambda is greater than 0, it goes to infinity and it's unbounded. One thing about solving this as well is we were to solve this in the time domain and we take the integral of this. It's actually really difficult to solve in the time domain. And this is where we turn to the Laplace transform, which is covered in chapter 2. It's just an easier way of solving this differential equation without going through the 4 different scenarios and guessing which solution works. When we use the Laplace transform, we can actually find the direct solution. It gives us a direct way of solving this equation. There's a second method of solving this differential equation is using state space form. And state space form is also great because we can take all these, no matter how many differential equations we have, like we have 3rd, 4th, or 5th order differential equation, we can solve it in the state space form like it's a 1st order differential equation, which will be covered in chapter 3. So the point I'm trying to drive across here is that chapter 2 and 3 are going to be tools that you use to help you solve and predict how a system will respond based off of the inputs and initial conditions. Are there any questions? I know it's really boring because it's very dry, but we have to go through it. So we can finally start on chapter 2, which is going to be Laplace transform. So basically, think of a Laplace transform. It's a tool. The Laplace transform is used to solve differential equations in the frequency domain. Uh, so the nice property about Laplace transform is that it explicitly separates the input and output of the system. And the more technical definition, it's an integral transform that converts a function of a real variable, usually in time, to a function of a complex variable, which is denoted by the complex frequency. So this is just the technical definition of it. I won't have you apply this definition. We'll just give you a table. You can just skip the integral part. But this is how we define it, where um, yeah, where S is equal to our sigma plus j omega. So this is our real component. And this is our frequency imaginary component, but this is also our frequency component. And it's in the imaginary domain. So the reason why this is in the frequency components in the imaginary domain is because when we apply Euler's equation to this, like e to the minus st, we're going to have a exponential decay or growth based off of the real component. And then the oscillation part is going to be omega here. And that's why it's in the imaginary component. One other note about this property is that, let's say I have, if we look at our block diagram in the time domain, we have R of t going into our differential equation, and then we get output C of t. When we take the Laplace transform of this whole system, it becomes R of s going into G of s, and then the output is C of s. So this is what we were seeing in the block diagrams where the s comes from. It's from the Laplace transform. And when they say you can explicitly separate the input and output of the system, we can rewrite this block diagram as C of s, which is our output, divided by our input, R of s, is equal to G of s. And that's how we explicitly separate it. So this is our output divided by our input. Our system right here. So that's what we like about Laplace transform, is that we can explicitly separate our output by our input. One last thing about looking at e to the minus st. I was telling you about this form e to the minus st. If we were to write that out, we get e to the minus real part plus j omega t, which is then equal to e to the minus sigma t times e to the minus j omega t. So that's just a property of exponential. And then we can rewrite this as e to the minus sigma t multiplied by, and we apply Euler's formula, which is cosine omega t minus j sine omega t. So basically we sub this into that equation there, we expand it, and you solve the integral. And that's how you can get something into the frequency domain. Does this form right here look familiar? Does it look like a underdamped response from the earlier solution, where we have a exponential term multiplied by a cosine term. So from the earlier slides, if we look at from the earlier slides, if we look at the four different solutions, it looks like this form here. Or sorry, last one. The underdamped system. Very similar form. So this is actually the general form, because if we have no damping, then omega is equal to, or if we have no oscillation, omega is equal to 0, and we just get e to the minus sigma t. If we have undamped systems, then sigma is equal to 0. Then we just get cosine and sine components. If we have critically damped, it's also equal to, where omega is equal to 0, we still have just the exponential terms only. So this is a general solution. So then the inverse Laplace transform is the reverse, where we take something in the S domain and we put it back into the time domain. So the inverse Laplace transform is an integral that takes a function in the complex variable to a function of a real variable. So just another way of saying we go from the S domain, which is the frequency domain, and we take it back to the time domain. And this is the formal definition of it. I wouldn't really worry too much about it. I'm just giving you the definition because you should just know that it exists. You don't need to know how to apply it. But just for thoroughness, I wanted to show you this. Any questions about Laplace transform or anything so far that we covered? Okay. So basically, this is the Laplace transform tables. This will be provided for you when you take your exam. The way Laplace transform works is we have the way we use it is we have our ordinary differential equation in the time domain. We take the Laplace transform of it. All it does is it just turns it into an algebraic equation. Once we get this algebraic equation, we kind of shuffle it around into a different version of that equation, but in a way we understand. Then we take the inverse Laplace transform, which is going to be the algebraic solution, and we get our solution. And it might not make sense, and we'll go over an example that shows all of these steps. Before we do that, I just want to show you the tables and how to interpret the tables. So here, this is our input in the time domain, and then this is the equivalent version in the frequency domain. So this is our impulse input or Dirac function. So it's like if I hit something with a hammer, if you look at it in the Laplace transform, or if you take the Laplace transform of a impulse input, it's just equal to 1. So if I were to take the Laplace transform of 3 delta t, that's just going to be equal to 3. Because Laplace transform is a linear operation. If you look at property 1, or no, not property 1, property 2 here, if we take a Laplace transform of a constant multiplied by something in the time domain, it's going to be that constant multiplied by f of s in the frequency domain. So this is using property 2. If we look right here, this u of t, and I don't really like that they don't explain it, but basically u of t is this, if f of t is equal to u of t, this is basically equal to 0 when, or u of t is equal to 0 when time is less than 0, and u of t is equal to 1 when time is greater than or equal to 0. That's what it means. So if I were to draw this function, it's 0, and then this is time equal to 0, and then it turns on. It's basically a function that turns on out time greater than 0. So think of U of t as a on off button. When it's less than 0, it's 0. When it's greater than 0, it's 1. This is U of t. So then here, when we see t u of t, it's a input that's dependent on time. So it increases as time increases in a linear fashion. The u of t is just there to turn it on when it's past 0. And this is called a ramp input. Oh, this last one's called a step input. And in the frequency domain, it's 1 over s and then 1 over s squared. And then this is called a parabolic input. And this is the equivalent version in the frequency domain. And then you can also have a exponential input, sine input, and cosine input as well. And this is the representation, the frequency domain on the right column. Are there any questions? So it's kind of hard to understand why this is important until you apply this on some examples, but I just want to show you some of the properties. On the right-hand side, just this is to really show you that property 2 and 3 is shows that Laplace transform is a linear operation. And these are some other properties. One thing to note is if you were to take the Laplace transform on a derivative, because we're going to be applying this on differential equations, note that it's going to be this multiplied by f of s minus the initial value of that derivative. So it's going to be right here, these two properties, where it's going to be this minus s multiplied by our initial value minus the derivative at that initial value. So just make note of that. When I have you do Laplace transform, if I tell you it's 0 initial conditions, then you can make this term here go to 0. But if it's non-zero initial conditions, then those are going to be constant values that you have to put in. And this is the generalized form of properties 7 and 8. Any questions? So I'm going to stop there for today, and tomorrow we're going to go over this example of applying Laplace transform, and then we'll move on to lecture 3, which is going to cover chapter 3, and I'll upload the lecture slides for lecture 3 today. All right. Thank you.